Hey, welcome back. So, I guess I caught you here because you want help with your homework. So what I'm going to do now is I'm going to go over the integration homework, and it's not too bad. So if you take a look at the integration problems here, actually, let me go ahead and get the recording started again. Start recording. Cool. All right, so if you take a look at these problems here, the first problem here says approximate the following integrals using a trapezoid rule. So this, we're just using one iteration of the trapezoid rule. So we take the two endpoints and then of the integrand at, you say, the far right of the integration interval and the far left of the integration interval. We take those 2 points, we average them, and we multiply by h. And that's the trapezoid rule, right? And so that's really just all we're doing for the first, like, for problem 1 and problem 2. The some of it you might not be able to compute by hand. So for instance, we need to figure out what cosine of 1/4 is. But overall, I mean, that shouldn't be too bad. And then we're going to do the same again with Simpson's rule. In that case, we're just going to be using 3 points, right? So we use a left endpoint, the right endpoint, and twice the middle endpoint, if I'm doing everything right. And then you multiply by some extra coefficient. I think it's h/3, and then that's it. That's the Simpson's rule. Now the next part, so the book distinguished between the trapezoid rule and the composite trapezoid rule. So they say the trapezoid rule is just when you use the entire interval and you just take that average and multiply by h. And now in this case, they're saying use a composite trapezoid rule, which is what they mean by that is they mean to segment the interval, just like what we did in lecture, and then use those segments and just use the average of each endpoint and multiply by h. And so that's what they're doing, and same thing with the Simpson's rule, etc. And so then they want you to compute the error formulas and etc. And that's all stuff that's straight from the lecture. So this should be fairly straightforward to do. A lot of it is just like straight hand calculations, only like averaging 2 numbers, and so it's nothing you should really be too concerned about being difficult. And again, some of this we're going to have to employ a calculator or MATLAB, but I don't want you to use that on the test. And so if I give you something like this, I just want you to execute the formula, but it should be numbers that you can compute by hand. All right. So with that, I think I'm going to go ahead and stop, and let's go ahead and jump into it. Okay, so let's go ahead and jump into this. So we're looking at numerical integration, outside if you can't tell. So hopefully it doesn't get too loud out here. So the first problem here, if you take a look, if my fingers don't fall off. So for number 1, they're telling us to approximate the integral, the following integrals using the trapezoid rule. Okay, so I'll just take a look at just a couple of these. It's really simple. I mean, basically, you know the trapezoid rule. So you have like a function, and you're taking a look at the trapezoid rule, and you want to figure out the estimate of the integral between a and b. The trapezoid rule just really connects these 2 points, and basically makes a trapezoid that we take the area of. If we call this function f, then the trapezoid rule is simply f of a plus f of b divided by 2 times b minus a, and that's it. So that's all we're really going to be evaluating here, and so let's do this in red. So for the first one is integral from 0.5 to 1 of x to the 4th dx, right? And so using the trapezoid rule, this is opposed to the composite trapezoid rule, which would be splitting it over several intervals. So here, just straight trapezoid rule. It gives us, so we have f of a, well, that's just 1 to the 4th, or f of b rather, actually, and then plus f of a, it's addition, so it doesn't matter what order we do it in, divided by 2 times b minus a. Well, b minus a is 0.5. So what does this give us? That gives us 1 plus 1 over 2 to the 4th, and so that's going to be 16, divided by 2 times 1 over 2 here. And yeah, so it's a whole bunch of powers of 2, really. So it's going to be 17 over 16 divided by 2, that's going to be 32, so divided that by 2 is 64, right? So there you go. All right, not too bad. So if we take a look at b, see if we can even do b. Yeah, b is doable. All right, so b is, let's do this in green. The integral from 0 to 0.5 of 2 divided by x minus 4 dx. All right, so if I take a look, this is going to be, say, f at a is going to be 2 divided by 0 minus 4 plus f of b. It's going to be 2 divided by 1/2 minus 4, all divided by 2 times 0.5, which is the distance between those two guys. All right, so we can go ahead and start evaluating this. So it's going to give us negative 2 over 4 plus, let's see, if I multiply top and bottom by 2, it's going to give me 4 divided by 1 minus 8. And then we have all of this divided by 4 because this is 1/2, so I can combine that with the other guy. All right, so continue on. This is minus 2 over 4 plus 4 over negative 7 divided by 4, and yeah, let's keep it going. So combining like term or finding common denominators. So it's going to be 14 plus 16 divided by 7 times 4, which is 28. And then this divided by 4. Alright, so that is 28, right? Yeah, okay. And so all of these guys multiplied by negative 1. 14 plus 16 is going to be, what, 30? So we have minus 30 over 28 times 4. So let's see, 4 goes into 30 twice. Sorry, not at all. And so we can cancel 2, so that's going to be minus 15 divided by 2 times 28. 2 times 28 is, well, actually 20. Yep, no. Nope, that's co-primed 15. Okay, so 2 times 28 now is going to be 56, I think. So there you go. Yep, and that's it. That's the trapezoid rule, and that's the answer there. So it's telling us that it wants us to find the error bound using the error formula for the trapezoid rule. And so let's see, just looking it up now. Okay, so okay, so using the formula, so this is jumping ahead to part 3 because all those other ones are more or less the same. So our step size h is going to be, so this is for, say, part A, is going to be b minus a, right? Because we're only taking one step. M is going to be the maximum of the second derivative of f of x over that interval, so over the interval AB. And yeah, so the error formula itself ends up being we're going to have f double prime of x, the maximum of that, over b over a to b, times b minus a, an absolute value over 2. Well, b minus a is always positive. And so f initially was x to the fourth. F double prime of x is in, well, say f prime of x is going to give me 4x cubed, and then I'm going to 12x squared for my second derivative. And so we know that this looks like this, right? And so if we take a look at the interval that we're looking at is 0.5 to 1. So the interval we care about is here 0.5 all the way up to 1, and we know it's an increasing function, so its maximum value is going to be here at 1. So so then I can go ahead and replace this guy here with this. So so we're going to say, so m ends up being 1 times 12, 1 squared times 12, and so it's just 12. And b minus a is 1/2, so it's 12 times 1/2 divided by 2, and that's not that great. Let's see, so the error is going to be about 3 units, whatever our units are measured in. So it's not the greatest, but it gets you an answer. The other one's going to be a little bit trickier if we want to try to do that. So we have, say, 2 over x minus 4, if I remember right, for part B. Yep. And so this is the integral from 0 to 0.5. And so this is 3b dx. And so yeah, so here we have f of x is equal to 2 over x minus 4. If we want to take a derivative, we get f prime of x is equal to 2 over x minus 4 quantity squared times -1. And if I want to take another derivative, I get f double prime of x is equal to 2 over x minus 4 cubed times -1 times -2. Okay. So this ends up being, say, 4 over x minus 4 cubed. And if we take a look at the graph of that, we're looking, we care about around the origin. And yeah, so we know we have a pole like way out here at 4, and so that's not going to be great. But otherwise, we're taking a look at x minus 4. So here we're going to be negative in this region, just because x minus 4 is negative whenever you're less than 4. And cubing that is going to keep us negative. And so so basically this is what this looks like. As x goes to infinity, we're going to 0, and we have no zeros otherwise. So, you know, using our old pre-calculus skills, this is our graph, right? And so then basically we're looking at the interval from 0 to 0.5, and it looks like even though that's the highest positive point, we're looking at the absolute value maximum, and so that's going to be here. So so m, which is equal to the maximum over, say, 0 to 0.5 of the absolute value of f double prime of x, is going to be equal to 4 divided by 0.5 minus 4 cubed in absolute value. And so that's going to be 4 divided by, it's going to be 1/2 minus 4, or 4 minus 1/2, so that's going to be 3 halves, which is what, 7 over 2 cubed. And so that's going to give us 8 on the bottom, comes up to multiply it by 4, which gives us 32, divided by was 49 times 7. That's going to be what, 63, and 7 times 4 is going to be 28, and plus 6 is going to be what, 34. So 343. Yeah, that number seems roughly right. And you know, vaguely, you can see this is going to be a little bit less than 0.1. So that's actually not too bad. I mean, generally, I mean, if you just look at this, I mean, like by the time you get to this region, it's probably pretty straight. So, so that's telling us, like, you know, it looks like we're not actually going to have too much variation there, and so our trapezoid rule is going to be pretty accurate if we just go ahead and fill in, you know, all this. So yeah, so let's go ahead and compute that then. The error bound, the error is now going to be 32 divided by 343. This isn't actually the error, but it's probably the biggest contributor. Times b minus a, so 1/2 divided by 2. So this is going to get even better. So we have 32 divided by 4. That's going to give us 8 over 343, and so it looks like this is going to be you know, roughly 0.025. So the error for even just using one step of the trapezoid rule here is excellent, and that's just because it is relatively flat in this area. Okay, cool. So let's go ahead and take a look at another problem. So, if we take a look at, say, 2 is more or less the same thing. You might just have to, they're all sines and cosines and logarithms and things like that, and so you'll just have to go ahead and, you know, use a calculator there. I don't expect you to use a calculator on the exam, so you should expect something more like a rational function, or at least values out of cosine and sine that should be able to evaluate. Something like cosine of pi over 4, which we know is square root of 2 over 2. You know, something like that. Now let's go ahead and take a look at another one. So it says repeat exercise 1 using Simpson's rule. So I'm just going to do this for part 1a. So I'm going to say 5, and I'm going to say, you know, redoing part 1a. So what is Simpson's rule? If you take a look at Simpson's rule, it let me just pull up the actual rule itself, just so I don't screw it up for you guys. So Simpson's rule basically is this: is you take your function and you have an interval. So you're going from a to b. You have some function here, and what Simpson's rule does is it takes this point, it takes the middle point, and it takes this point, and the idea is that it fits a quadratic function that interpolates these 3 points, and then you compute the area underneath the quadratic. So if we call this, say, f1, we call this, say, f2, and we call this, say, f3, then the Simpson's rule is going to be this. It's going to be f1 plus 4f2 plus f3, and then we multiply it times b minus a divided by 3. Okay, so here, basically what we're saying is that this is, so when we say Simpson's rule here, we don't mean the one where we split up all the intervals and you just divide it into chunks of 3 points each, and then go ahead and calculate those individually. That is what we're calling the composite Simpson's rule in the homework. And so here, when we say Simpson's rule, we just mean use these 3 points and compute something. And so for 1a, remember, it was integral from 0.5 to 1 of x to the 4th dx. And so in this case, we're going to have f of x is going to be x to the 4, f of, say, and if I were to say f1, I'll say it's going to be f of 0.5, which is equal to, say, 1/2 to the 4th power, which is 1 over 16. F2 is going to be f of, say, 0.75, or 3/4, so 3/4 to the 4th power, and so we're going to have over 4 over 4 to the 4th power, 4 times is 64, right? So that's going to be 64, and 3 to the 4th power is 81, right? And then we're going to have f3, which is f of 1, and that's 1 to the 4th, which is just 1. Okay, so now we want to go ahead and compute these. Very nicely, we have a 4 here, and this is 4 to the 4, so those will cancel pretty nicely. So if I go ahead and take f, so we're looking at f1, well, I already have it written. So let's go ahead and get using Simpson's rule. Simpson's rule. This tells me that we have 1/16 plus 4 times 81 over 64 plus 1, and then all this times b minus a, which is 1/2 divided by 3. Okay, so now what I do is I go ahead and I take 1/16. I have 81 over 16 plus 16 over 16, and so it's equal to that times 1 over 6, and this is equal to so it's 81. Sorry, mosquito. So this is 81 plus 1 plus 16. So it's going to be 96 plus 2, 98 over 16. And then we just need to figure out what 16 times 6 is. And that is going to be, say, 36. So 3, 6, so 96. So it's 98 divided by 96. And so it's roughly 1. And so there you go. That's Simpson's rule. Okay. So not too bad. So then they want to know what is the error after doing Simpson's rule. Let's see. So I'm just looking it up so I can go ahead and put that in. So the error committed by Simpson's rule, I think this is part 6 or whatever. Yeah. So Simpson's rule error is basically h to the 4th, which is our step size, divided by 90 times f to the 4 c. Well, the maximum over AB of f to the 4th power of x divided by well, that's it actually, not divided by anything. Okay, so the 4th derivative, I should say, not 4th power. So if I take a look at f of x, in this case was x to the 4th, f prime of x is equal to 4x cubed, f double prime of x is equal to 12x squared, f triple prime of x is equal to 24 times x, f the 4th derivative at x is equal to 24. So this is pretty easy to work out then. So h itself is 1/2 in this case. So for 1a, we have h is 1/2, and that's raised to the 4th power divided by 9 times 24. And this is actually looking pretty good. So it's going to be 1 over 16 divided by 9 times 24, and so yeah, 24 is 8 times 3, and so 16 is 8 times 2, so that's going to leave us 3 over 2 times 1/9, and that it leaves us with 1 over 6, and yeah, that's the error committed by Simpson's rule. Okay, so that's not too bad. So I'll give you a sketch of how to do the next couple. So it's talking about the composite trapezoid rule and the composite Simpson's rule, and it's more or less the same thing, except you just have to do it with a little bit more work. So here we're looking at 1A for composite rule. So if you look at the PDF for the homework, this is actually the second chunk of the integral homework. And so we're saying that we're taking a look at the integral 1 to 2 of x ln of x dx, and we're looking at the trapezoid rule. so the composite trapezoid rule. So I'm basically, they said use n equals 4 here. So then what that's going to give us is going to give us a step size of h, which is going to be 2 minus 1 over n. And so here n is 4, so that's going to be 2 over 4, a step size of 1/2. So we're taking the integral from 1 to 2. Sorry, oh, no, that should be a 1 there, and step size is 1/4. Okay, sorry, I knew something was wrong. So basically, this is a 1.5, this is 1.25, this is 1.75, right? And x ln x, I think that honestly stays pretty straight. There we go. And so that's what we're gonna get. And so yeah, if you want to do the trapezoid rule for this set, basically you're gonna use these points here, and yeah, that's what you get. And so we have 4 regions that we're taking averages over. Natural log is going to be hard to compute on your own, so just have a hand calculator out and you can do that. But yeah, that's basically where you're going to get. So just use those points, and basically what we're going to do is we're going to have, say, f of 1 plus f of 1.25 divided by 2 times our h, so 1/4, plus f of 1.25 plus f of 1.5 divided by 2, and this times 1/4, plus f of 1.5 plus f of 1.75 divided by 2 times 1/4, plus f of 1.75 plus f of 2 divided by 2 times 1/4. Right, and whatever this is, that is the answer to that question. So what will you do if you, and then when you want to talk about the error, again, so if you take a look back here when we wrote it down, the Simpson's rule error, not Simpson's rule, but the error we got for the trapezoid rule came from here. But instead of b minus a over 2, this is going to be replaced by h. And so h we know is 1/4 now. So coming back all the way over here, so we know that h is 1/4, and the error is going to be bounded this way. Bound, so the error could be closer, but this is the best bound we can work out. It's going to be f double prime of x, and take the maximum over over the interval 1 to 2 times h divided by 2, h squared divided by 2. I think. Did I get that wrong? Hold on. I think I got that wrong. That should be h squared. Sorry. Yes, that totally should have been h squared. That's stupid. Alright, so that should have been h squared. There for b minus a, so that's 1/2, and so that should be squared, so take this guy divided by 2. Sorry, my mistake. And the other one I think I got right with Simpson's rule. Yeah, h to the 4th. Okay, that's fine. Okay, so this should be a squared, and so now we can go ahead and compute this. So we still need to figure out, I'm just going to call this m. So it's going to be m times 1/4 squared, so that's 1/16, so 1 over 32. So, because we're dividing by 2. So I just need to figure out what m is. Now m is going to come from the second derivative of x ln of x, so f of x equal to x ln of x, and we can figure this out with product rule. F prime of x equal to ln of x plus x times 1 over x, so that's equal to ln of x plus 1. F double prime of x then is going to be equal to 1 over x. Okay, so we're trying to figure out the maximum of this over the interval 1 to 2, and this is simply this. And so it looks like its maximum value is going to happen here at the left endpoint. So, and we know that f double prime of 1 is just 1, right? So the error is going to be 1 times 1 over 32. So it's 1 over 32, right? That's where I left. Yep. And so, yeah, that's actually pretty decent. Again, this doesn't seem to vary very much over that interval. And honestly, the contribution of a logarithm is going to be pretty minimal over this area. So I mean, the idea is that this is actually pretty straight. So so we're again not going to be contributing too much errors here. Okay, cool. So Simpson's rule, how does that differ? So if we talk about the integral from 1 to 2 of x ln of x dx, and we're using the composite Simpson's rule for n equals 4, for instance, again, we're still left with h is going to be 2 minus 1 over n, which is equal to 1/4. And so just drawing out a graph again. So again, h is going to be 1, 2, 3. So we have 1, 2, and then these individual points are going to be 1.25, 1.5, 1.75, and so yeah, our graph is going to look something like this. And then our points that we care about are these guys. Okay. So, but what happens with the Simpson's rule is we divide the interval differently. We chop it like this, and then we have these 3 points, and then we have, say, these 3 points. And so these are each going to be used independently. So, yeah, set in green and blue. So, so then what we're going to do then is we're going to have f of 1 plus 4 times f of 0.5. Sorry, not 0.5, but 1.25. Plus f of 1.5, and then this divided by 3, and then times h, and then for the other piece, we're going to have, now let's do this in green, we're going to have f of 1.5 plus 4 times f of 1.75 plus f at 2, and then all this divided by 2 times h. And just go ahead and work that out with a hand calculator, and then that'll give you your answer. So then now if we want to compute the error, remember the error itself is going to be come down to h to the 4th times the maximum, the 4th derivative of x, f of x, from 1 to 2 divided by 90. Okay, well, h here is going to be 1/4, and so it's going to be 4 to the 4. Well, 4 cubed is 64, so it's going to be 240, 256. So it's going to be 1 over 256 times 1 over 90 times the maximum of the 4th derivative of x over that interval. So let's just go ahead and take a look. The second derivative, second derivative is 1 over x. And so we have f3 of x is going to be negative 1 over x squared, and f to the 4 of x is equal to 1 over x cubed. Well, minus 2 over x cubed. And so, or 2 over x cubed, sorry. So then if you wanted to find the maximum of that over the interval, that is again going to happen at when you put in 1, so f4 of 1, because this is just a decreasing function. It's going to be 2 over 1, and so it's 2. Right, so so then what we get then is going to be 1 over 256 times 1 over 90 times 2. So if you want 1 over 128 times 1 over 90, and we'll just say it's very small. So there you go. So if I was to put this on the exam, I would either give you nicer numbers to work out, or you can just leave it like that if it's a free response. Okay, cool. So that's Simpson's rule, a composite Simpson rule, in addition to the other ones. So the composite Simpson's rule, you have to group everything to 3s, and that is the big difference between that and the trapezoid rule, where you have, just every pair, consecutive pair ends up being grouped together, and you apply it, the composite Simpson's rule, chunks of 3. Okay, so yeah, that's good. And that looks like that was it for that homework. So while I'm here, I might as well just go ahead and do a couple problems out of the other ones, because I don't know if I'll have time. So I already posted some solutions, for my exam review for my differential equations class, because these problems come straight from my differential equations class. But you might as well just work out a couple. And so yeah, so here we're going to try Euler's method for solving initial value problems. So in general, we're going to have, say dy dt is equal to f of t comma y, and we're going to have, say, y of 0 is equal to y naught, right? And we know that if we want to we define, say, yn plus 1 should be equal to y of n plus h times f of y tn yn, where we say that, I should say not 0, but starts at t naught. And so we say that tn is equal to t naught plus h times, say, n, if you like. And so, and h is some fixed positive number that you start with. So go ahead and trying out, say, number 1 out of the homework. We have dy dx is equal to negative x over y. So this ends up being my f of xy. So instead of t here we have x. And then they're asking us to approximate the solution to the given initial value problem at the points x equals 0.1, 0.2, 0.4, and 0.5 with a step size of 0.1. So I'll do the first couple for that. So here we're saying that h is equal to 0.1, and when I find an estimate of y at x equals 0.1, 0.2, and let's see if we're brave enough for 0.3. I'm not sure if I will be, but yeah, let's go do it. So here we say y of 0. Actually, we need that. So the problem says y of 0 is equal to 4. So y of 0 equals 4, and then y of 1 then is going to be 4 plus h times f of 0 is where we started, and then I'm going to put 4 in for y. And so that's going to be 4 plus 0.1 times negative 0 divided by 4, right? And so it's just 4, because that second term is 0. And so this should be roughly y of 0.1, right? Y2 then is going to be 4 plus 0.1, that's our h, times negative, now our new x that we're at is 0.1, because that's where this guy is. And then we're going to put 4 here. Okay, so it's going to be 4 plus, or say minus 0.01 times, say, 0.25. And so this is going to be 4 minus 0.0025, which is going to be 3.9975, I think. Yeah, that works. And yeah, so there you go. Not a big difference, but that is the answer. And so this is at y of 0.2. So that's roughly what that is. And yeah, you can keep that going, get a hand calculator out and start doing it. I wouldn't expect you to do any more than what I just did here on the exam. So yeah, because on the exam I don't want anybody to have calculators. Okay, so that's good. And so yeah, you can continue this on. It's more or less the same thing. I mean, you guys have had differential equations, so it should be pretty straightforward. there's one problem that was a little different. I thought this was kind of a fun problem. So number 12. So basically what we're trying to do is we want to show, start with this guy, say dy dt is equal to y, and starting with y of 0 is equal to 1. Now we know from differential equations that means that y of t is equal to e to the t, right? And so we want to show that using Euler's method, with step size 1 over n, we get this. So y of n is equal to 1 plus 1 over n raised to the nth power. Now this is coming straight from our compound interest formula, and it says, for n equals 1, 2, 3, etc. Okay, and so and keep in mind here, yn, when you use step size n, should be roughly what y of 1 is, which should be, in this case, e to the 1. And so we see that here, using the convergence properties of the exponential of the Euler's method, as n goes to infinity, we converge to the e. So here you can actually use this to prove this, combined with the error formula for the exponential. You can use this to prove the convergence of this to e, which is pretty nice. So then let's go ahead and prove that yn then is going to actually be this. This is pretty straightforward. So if we go ahead and we start, so we're gonna let. Oh, that's cool. Hold on, 1 second. Apologize for the interruption. Just caught a couple hawks flying around up here, so I thought it was pretty cool. Anyway, I think I recorded without my mic on, but well, that's what happens. Okay, so let's go ahead and get started. So here we're taking step size of 1 over n, and we're starting off with y of 0 is equal to 1. So then if I go ahead and take a look at y1, then should be equal to y naught plus h times f of, say, 0 comma y naught. And, well, that's y naught plus h times, well, y naught. And that is equal to y naught is 1, plus h is 1 over n, and then times 1, right? So that's what we get for the first time. If I take a look at y2, then I'm going to have, say, y1 plus h, which is 1 over n, times y1, because that is just what f of the function is, or if we want f of y1, and so then that's going to be 1 plus 1 over n plus 1 over n times 1 plus 1 over n, and that is equal to, we'll factor out 1 plus 1 over n, you get 1 plus 1 over n times 1 plus 1 over n, and so that's 1 plus 1 over n squared. And then by induction you can prove that this works for 2, etc. And so that means that yn should then be 1 plus 1 over n to the nth power. Right, so, and that is exactly what we were trying to prove. And so, so I can say this by induction. I think by this point, most of you guys should be fairly comfortable with the induction argument. But yeah, so there you go. And then basically what that means is that, this is going to end up converging to, e. So something that might be fun to do is to use the formula for convergence of the of this term, and see how quickly this actually converges to e. I think it actually converges fairly quickly, but yeah. Okay, so we have one more group of problems to look at, and that is for Picard iteration. Let me see if I can pull that up. And here we go. Okay, so Picard iteration. Okay, so let's go ahead and talk about what Picard iteration is. All right, so I linked you back to my differential equations lecture on this because, I mean, I just want you to have the algorithm and I don't care about showing it converges or not. But the idea here is that you're trying to solve again, say dy dt is equal to f of t comma y, with y of t naught is equal to say y naught, and so yeah, the idea is that you're just trying to make up a sequence of guesses, and so you start off with some phi naught of t, and you're guessing that maybe that should be equal to just y naught, and then you guessed f phi 1 of t should then be y naught plus the integral from say t naught to t of f of t phi naught of t dt, and then phi 2 of t should be equal to y naught plus the integral from say t naught to t of f of t comma phi 1 of t dt, and etc. And the idea is that as you keep working it out, you should get closer and closer to your solution. The truth is that this only really works in a small horizon, but it's a nice initial attempt at this. And another thing to note is that you'll never be able to solve anything that is not a polynomial, because you need to be able to integrate it at the end of the day. If you start having sort of non-polynomial or transcendental functions, you start plugging in transcendental polynomials in there, they start to get really hairy, really quick. So let's go ahead and take a look at one or two problems here. So starting off with problem number 1, they give us dy dt is equal to 2t minus y squared with y of 0 is equal to 1. I think I actually had all these problems starting at 0, and so maybe I'll just keep that consistent for the exam. I think actually in my lecture I forgot to put t naught here, I put 0. So that's one slight difference, but it's really just a shifting of the whole problem, which is fine. So we start off with this, and we're trying to use Picard iteration in order to get an estimate. So we start off with phi naught of t should be equal to 1. That is our y naught here. And then next one should be phi 1 of t is equal to y naught plus the integral from 0 to t, because we're starting at 0, of say f of t comma phi naught of t dt. And this is 1 plus the integral from 0 to t of 2t minus say phi naught, which is just 1, squared, and all this integral dt. And so this is 1 plus let's do this integral. So integral from 0 to t of we're gonna have, or well, I guess I should have tau here, right? Because the external variable on the other side is t. So keep my variable straight. And so yeah, we get 2t, that's going to be tau squared, minus 1 squared is just 1, so that's going to be tau, and valuing this at t and 0, so it's going to be 1 plus t squared minus t. Okay, cool, so that's phi 1, and so that's one iteration, and say phi 2 then of t is equal to say 1 plus the integral from 0 to t of f of tau comma phi 1 of tau d tau, and then this is going to be 1 plus the integral from 0 to t of, let's see, we have 2 tau minus 1 plus say tau squared minus tau plus 1 quantity squared d tau, and this is probably as far as I'm going to go. So 1 plus integral from 0 to t of 2 tau minus, all right, so this guy squared. All right, let's go ahead and take a look. All right, so we have tau squared minus tau plus 1 tau squared minus tau plus 1, and multiplying all these together. So we're going to end up having, say, tau squared, tau to the 4th, minus, I really don't want to do this, tau to the 4th minus tau cubed plus tau squared. So this guy multiplied times each of these. Now we have minus tau cubed plus tau squared minus tau, and that's this guy times each one of these. And now we have plus tau squared minus tau plus 1. Okay, and so all of these guys together gives us, we have tau to the 4th, we have 1, 2 minus 2 tau cubed, we have 1, 2, 3 tau squareds, I should probably put the number there, 3 tau squareds, and we have plus 1. Oh, and 2, sorry, minus 2 taus, and then we have plus 1. All right, and so we have, putting all that in here, so we have tau to the 4 minus 2 tau cubed plus 3 tau squared minus 2 tau plus 1 d tau, and this is equal to 1 plus the integral from 0 to t of, so it's going to be t to tau 4 minus 2 tau cubed plus 3 tau squared minus 2 tau, well now, minus 4 tau plus 1, and I'm pulling out a minus sign out here. All right, d tau, and doing all of this, let's scoot this up so I have a little bit more space. There we go. And so ultimately we can go ahead and write this out. It's going to be 1 minus t to the 5th over 5 minus 2 over 4 t to the 4th plus, oops. Right, so it's minus there plus that. Minus signs always get me. Minus 3, well, actually it just becomes t cubed, and then we have minus plus 2t squared plus t. There we go. All right, and so that was that. And then it asks for 3 iterations, but I'm stopping at 2. If you want, go ahead and, I mean, I'm trying to keep the exam manageable, so I might not ask you to do this many. Or if I ask you to do a third one, it should be a lot easier than this. Not that this is hard, but just squaring that guy is going to be a real pain in the ass. So yeah, I'm trying to keep things not be a pain in the ass on the exam, but I guess that's all subjective. Okay, so on the 5th one, I don't know. I don't. It's not going to be on the exam, and I don't feel like reviewing it right this second. And so yeah, maybe we'll stop here. So one thing else I want you to know, is basically, well, I really am going to stop here. Do I want to go elsewhere with this? Yeah. Okay, maybe we should go ahead and just talk about this. Just in case I get some random itch to put this on the exam, and this is something that came out of the lecture. So here's one thing that you should keep in mind. If the Picard iteration is, so basically if you find that your phi of n is equal to phi of n plus 1, then that means that phi of n is a solution to the initial value problem. Right. So for instance, if I chose phi not to be constant, but I just say e to the t in this case, and I consider my initial value problem, say y prime is equal to y with y is equal to 1, y not is equal to 1, so being y of 0, then what we get is this. We have phi of 1 is going to be equal to 1 plus the integral from 0 to t of e to the t dt. And if we go ahead and we work that out, it's going to be 1 plus, or say e to the tau. I did that again. So that's going to be e to the tau integral evaluated at 0 and t. And so it's going to be 1 plus e to the t minus e to the 0. And that is just e to the t because this guy cancels with this guy. And then that basically means that e to the t is a solution to the initial value problem, which is fairly nice. So that's a nice thing. I threw this into my differential equations 1 exam, and so potentially I could throw this into this exam too. Might be a little bit more of a complicated integral than just this, but nothing that shouldn't be manageable with some standard calculus 2 techniques. Okay, so I think that's good. I'm freezing my butt off. I can't feel my fingers, and I think I should probably end it here. All right, thanks for watching, and we'll get back to the office. Okay, so that was numerical integration. And so that rounds out the first chunk of homework I gave you guys. There's still a couple more problems that we have lingering, just for initial value problems and stuff like that, and I'll make a video on that one too. And with that should be everything for the final exam. So the final exam is more or less based on this homework. So if you feel comfortable doing these homeworks and following along with the lecture, I'd say you're pretty set for the exam. In any case, so good luck, and if you have any questions, of course, email me. I try to be really snappy with my email responses. I think I have 1 or 2 lingering that's been a couple days. I'm sorry about that. I usually try to get back within an hour. But yeah, I think we should be good. And with that, honestly, that's really the end of everything I'm going to be testing you on the exam. And so thanks for watching and hanging in there with this class. Hopefully the final exam isn't going to be too trying for anybody. And I just want everybody to have a nice, smooth exit. We're in COVID times, and it hasn't been easy for anybody. I have been tremendously stressed myself, and I just do my best to keep up with you guys. But yeah, thanks for hanging in there, and have a great holiday.